All right, so I gave you guys a handout. So this handout here is a bit about proofs and proof writing. Okay, so the front is kind of a guide of. So if you don't know where to start, so you see a proof, and I'm like, prove this. Okay, and so here it'll have like the type of thing that you're trying to prove, and then it'll have a list of ways to prove it. Okay. And actually, there's only so many ways that we have for proof techniques. There's a finite number of proof techniques in math. Well, I mean, of course, other than like constructing crazy objects. But like, yeah, so this is a good guide for you guys if you guys get stuck. Also, on the inside, there's a little bit about writing proofs. So proofs are like writing essays. And here, I would like you guys to read this about how to write a good proof. Okay? Okay, and then on the back, here are some formal rules of inference. Okay, so if we get to a point where we want to prove things about proofs, so that's what mathematical logic is about, then we're going to use these things. So these are kind of the basic rules of inference here. Yeah, okay. So I just handed back homework 2, and I have some comments. So I graded a subset of them. I graded number 1, number 2, and number 5. Okay. For most part, number 5 was good. And you guys can resubmit Friday if you want to get some points back. And so I have some comments on the homework. Okay, so comments. On homework 2. Okay, so regarding the first one. Okay, so the first one asked to prove one of the De Morgan's laws, assuming the other one. Okay, and so what I saw one of you guys do, a lot of you guys do, was assume the statement and then try and manipulate both sides. And so let me, so you take an equation and then you'll try and do something to both sides. And so let me tell you that this, you manipulate it until you arrive at two things that are equal, and then you're like, okay, since these two things are equal, then the original thing that I supposed must have been equal. Okay? So that's not a valid way of proving something. So you can't assume what you want to prove in a proof and then manipulate it to get something true. And conclude, what you originally supposed was true. Okay, that's kind of long-winded, but so let me give you an example of a bad proof. Okay, so let's look at this technique a little bit, where we take something and then we manipulate it line by line. Okay, so let's suppose that -1 is equal to 1. Okay, so this is what some people do. You know, they'll take something, and then here, let's square both sides. Okay, so suppose this. So -1 squared is equal to 1 squared, right? So this is 1. This is 1. Okay, so since 1 is equal to 1, what we must have -1 is equal to 1, right? So here's an example of something where you can take something, right, and manipulate it to get something true, but the original thing that you supposed was false. Okay, so don't do that, right? All right, so this is a bad proof. This is bad. Not bad as in like good bad, but as in wrong bad. Okay? Okay. So, all right, so I just wanted to say this. So you should just be using the rules that we have for manipulating things. So regarding number 2, okay, so here, recall that I asked you guys to write this sentence: every natural number greater than 2 is prime or has a prime factor. Okay, so I'm going to label this for future reference here. Okay, so I asked you guys to write this out in symbols, and I gave you guys some symbols. So let me show you how to do this correctly. So the answer, the solution here, is as follows. So it says for all natural numbers, okay, if the natural number is greater than 2, it's an if-then statement. So you could really say that for every natural number, if the natural number is greater than 2, then it's prime or has a prime factor. So this implies P of n, or there exists some m in the natural numbers such that, well, P of m and m divides n. Okay? So this is the statement we have here. So, okay, so this is the same thing as has a prime factor, meaning that there's a number which is prime and divides n. This is an m, and this is an m. M. Yeah. Okay. So I gave you guys some symbols. So in symbols, the symbols I gave you, or some notation that I gave you, were the following, right? I wrote n of x. So this is the predicate. X is a natural number. And the ordering might not be exactly as we did it, but we'll do it like this. X is greater than y. So it might be g of yx. But for today, let's just do g of xy. We had g of xy. X is greater than y. We had p of x. So x is prime. And then we had r of xy. So these two here are relations. So this is x divides. Okay, so these were these predicates and relations that we had. Okay, so here, so there was some confusion about the symbol about n of x. Okay, so n of x is really the same thing as x is an element of n, right? And so some people wrote, so there's a mistake. A common mistake was that people wrote things like x was an element of n of x. Okay, so this is like writing x is an element of true, right? So that's something that people wanted to do, right? So there's a way of going between this n of x thing and, so this is not a thing that you can do, okay? But there's a way of going between the two, right? So so here's how I'm going to say something to clarify how we can go between the two. So here's a clarification on quantification over sets. Okay? So if I want, so if, I don't know, here's a big phi. So phi of x is some predicate. And S is some set. Then the statement for all x an element of S, phi of x. So this thing is really by definition, so this is by definition. So this is really saying that for all x in our universe, x is an element of S implies phi of x. So that's how you can convert between the two. So in particular, if we have a predicate for here, instead of saying for all x in the natural numbers, we could say x is in the natural numbers and then whatever the proposition is that follows. Okay? Also, we have this one. If this, so the existential quantifier, right? This is by definition. So there exists an x in the universe. So this goes over all the universe, such that x is an element of S and phi of x. Okay? So this was in the book, but I wanted to clarify about switching between the two. Okay? So what does this mean, right? So in our statement here, right, in our application, so you notice how I wrote it like here, for all n in the natural numbers. So this means, right, so this is this little side thing here. So this means we could have wrote something like, you know, for all x in the natural numbers, blah, where this thing here is blah. This is blah. Right? I guess this whole thing, right? Right? This is what I mean by blah. Okay? So for all x in the natural numbers, this, or I could have written, or for all x, n of x implies blah. Okay? So we could have done it like that. So, all right. So, all right. So I added some homework exercises related to this type of switching for the next homework. So here's some exercises related to this, so that you guys get some more practice to this. All right? Okay. So is there any questions on this? So, okay, so the other thing that I didn't do is I wrote that all out without using the g of x, r of x thing. So instead of writing the divide sign, I would have written r of xy, right? Or r of, you know, I think I had m divides n at some point. So instead of writing m vertical line m, or m vertical line n, I would have replaced that with r of mn. Does that make sense? Instead of writing x is greater than 2, I would have written g of x2. And that was another way you can do it. And if you wrote it in the symbols that we used and just ignored those symbols, I accepted that as well. Okay? Any questions on this? Okay. All right. Okay, so in the previous class, we talked about commutative rings. Okay, so what was a commutative ring? a commutative ring. Okay, we talked about groups. Groups were things with an operation which was invertible. Then we talked about abelian groups. Those were commutative groups where the operation is invertible and we usually use the sign plus. Okay? So once we have an abelian group, we could add another operation, right, which is a multiplication. And then you have a multiplication and an addition, and you have like distributive properties, associative properties for both these operations, a 0, a 1, right? And then you have distributive properties. Did I already say distributive properties? I don't think I said that yet. So then you just get a thing that looks like the integers where you have a plus and a times. And then you have some axioms that these obey. And that's what a commutative ring was. And we gave some examples. OK? So today I just want to start with proofs. And I'm going to do some things about divisibility. So let's do. So divisibility and properties of rings. Okay, so I'm going to start by doing a proposition. So, okay, so let's let R be a commutative ring. Okay, then for every A an element of R, A times 0 is equal to 0. Okay, so I want to prove this from the axioms. Okay? Mm-hmm. It's an A. It's an A. Yeah, it's an A. So if my writing gets confusing, let me know. Yeah. Okay. So, all right. So here's a proof. A proposition is just like a theorem. It's a mathematical statement that we want to do. And so we're assuming the axioms for commutative rings. Okay. So what can we do? So here we need to show that A times 0 is equal to 0. Okay. So let A be an element of R be arbitrary. Okay, so that's usually how these for all statements go. And you can see that, you'll see that in the handout that I gave you. You'll see a for all statement, and then it'll give you, this is what you have to show. Okay, and now there's a little bit of trickery, right? But here we'll write A is equal to A times 1. Okay, so this is by the multiplicative identity property. Okay, so this is also equal to A times 1 plus 0, because 1 plus 0 is the same thing as 1, right? So this is by the additive identity, right? The axiom for the additive identity. And then we have a distributive rule, right? So it says that A times 1, this is equal to A times 1 plus A times 0. Okay, so this is the distributive property. And so then we'll just use the additive identity again, A times 0. Okay, so this gives this equality. A is equal to A plus A times 0. Okay, and we want to show that this is 0. So what can I do to this thing to get that this thing is equal to 0? Subtract an A. And why can I subtract an A? What does it mean to subtract an A? Subtracting an A is really adding an additive inverse. So we're using the additive inverse property, right? So the additive inverse property says that for every element of the ring, there exists another element of the ring which adds to 0, right? And that allows us to subtract both sides by additive inverse axiom, right? So there exists some A inverse, right? Such that a plus negative a, or a inverse is 0. Okay, so adding minus a to both sides of, let's call this equation star here, gives a plus a minus a, or you could just write this as minus a if you want. That's what we mean by minus a, is equal to a plus a times 0 plus a minus a. Okay? And so this thing here, this line is the same thing as 0 just by using that that's equal to 0. And then this thing here, this one plus this one is 0. And this is a times 0. Okay? And this finishes the proof. The proof. Okay, so we showed that 0 is equal to a times 0, just kind of manipulating the axioms. Does that make sense? Okay. Okay, so that's just what I wanted to say. Let's go back to the divisibility statement we stated last time. And if you have questions, just feel free to blurt out. Here?
Yeah, do we have to signify after we prove that because those two are equal, the proof is complete?
Yeah, it would be nice if you did that. I mean, if it's clear from the context, but once proofs get more complicated, sometimes you start writing something really complicated, then you forget what you were doing, right? And you're like, oh yeah, this is what we were supposed to be doing the whole time, right? So it's nice. It's nice to the reader to do that. Yeah. Okay. So, so last time we had some divisibility properties. So we had this proposition. This in parentheses just says, talks about saying what the proposition's about. So let A, B, C, an element of R, be arbitrary elements of a commutative ring. Okay, and then we had the following properties. So if A divides B and A divides C, this implied that A divides B plus C. This is one of the properties. And then I'm just going to copy the rest down. So A divides B implies A divides B times C. 3, A divides B and B divides C implies A divides C. So this property is called the transitive property here. So here, this divides thing is really like this R of xy. It takes two things and then it spits out true or false, right? And so this is saying if A is to B and B is to C, then A is to C. So that's what we call the transitive property sometimes. And so in the homework, I give you guys an example of another, what's called another relation, and I'll have you guys show it's an equivalence relation. So it proves a bunch of properties that are similar to this one. So, so if A divides B and A divides B plus C, then A divides C. Okay, so let's take these properties here, and we'll do a proof. Okay, so I'm going to do the first two properties, right, and then I'm going to have you guys do the other properties as an exercise. And then I'll help you guys with it. Okay, and so most of the proofs that we do, like the thing that you have to ask yourself all the time is like, what is the definition of what we're trying to do? So this is the thing that we suppose. So you look at the table again. And then supposing this, we need to conclude this. Okay, so let's do the proof of the first property. Okay, suppose A divides B and B divides, or A divides C. Okay? So now we apply the definition of A divides B and A divides C. So by definition, so this is the definition of divisibility, B is equal to A times B prime, and C is equal to A times C prime for some B prime, C prime in the ring R. Okay? So this means that there exists some B prime and C prime such that B is equal to AB prime and C is equal to AC prime. Okay? So now we want to conclude this B plus C, A divides B plus C. Okay? So let's just write down what B plus C is. So B plus C, okay? So this is equal to AB prime plus AC prime. And we're just using these two properties here. Okay? And so this is equal to A times B prime plus C prime. Okay? So now this shows that B plus C prime is divisible by A because it looks like A times some stuff. That's the definition of divisibility. Okay? And so we're done. So A divides B plus C by the definition of divisibility. And we are done. Okay. Any questions on the first proof? Okay, so let's do the second one now. So proof of 2. So what do I write here? So how do I start? I would start with suppose A divides B. Then it's really formulaic, right? So this is an implication, so we suppose this, and then we're going to conclude the result. All right? Suppose A divides B. All right? So, by definition, B is equal to AB prime for some B prime in element of R. Okay? And now we're supposed to conclude that A divides B times C. Okay? So B times C. So this is equal to AB prime. I'm just replacing what B is times C. And so this looks like A times B prime C. So by definition, A divides BC. Right? The definition is that there exists some x such that BC is equal to A times x. This is the x. Okay? So it looks like A times some stuff, right? And this is the stuff.
How does B prime equal B?
B prime does not equal B.
So then how are they equal?
So prime does not mean derivative at all. That's what you're. Prime is just another symbol. So prime just means I wanted to make a new letter. It's somehow B-ish, right? And so I just put a prime on it, and it's a new symbol now. It doesn't mean derivative at all. It just means. Yeah, exactly. It's just a new symbol, B prime, right? Okay. Yeah. And that's what we wanted to show. Okay? So okay. So before going, so for here, let me write the exercises down. So the exercises are, exercises. Okay, so finish 3 and 4 of the above. Okay, and then on handout 2, section 1, right, do the following. Do 1, 1, 2, 3AB, 3A, 3B, and 4. Okay, so I want you guys to do those. And for these exercises, there's some properties of the integers that you need of z. Okay, so let me write. I have them written down here, and we'll talk about them a little bit more later. So the properties of z are the following. So the only units. So let me put it this way. So if a times b. So if a times b is equal to 1, this implies a is equal to 1 or a is equal to minus 1. Okay? So the only things that have multiplicative inverses are 1 and minus 1. Okay? The other thing that we need is that, so if AB is equal to 0, this implies that A is equal to 0 or B is equal to 0. Equivalently, if A times B is equal to A times C, this implies that A is equal to C, or sorry, B is equal to C, or A is equal to 0. Okay? So this is an equivalent property to this one. And you could prove that these two things are equivalent. Okay, so that's something that you could try and do. This would be true for an arbitrary ring. Okay, commutative ring. All right, and I think that's all you guys need. So I'll have you guys work on these, and then I'll come around and help you guys.